All right, so we're going to do and learn about proofs with identity. And number 5, on our paper looks like this. So with proofs, there are some formalities that we follow. And in general, there are some acceptable formalities out that we can do for proofs, but what we're going to do is every time we have a proof, we are going to first separate the left side and the right side with a line. Because it's an automatic 1-mark deduction if you assume a proof is true before you prove it. So if you use equal signs too early, it can be a 1-mark deduction. So we try to avoid that by where the equal sign is drawing a line. And it becomes a puzzle. The puzzle is you want the left side and the right side to be identical. Right now, they are not identical. On the right side, we have a 1. On the left side, we have a cos t and a secant t. And what you're allowed to do is you're allowed to use any of these formulas that we've learned already, any formulas that are on your formula sheet, and we'll be adding some as we go. These are your tools that you're allowed to change. So this means if you see a cosecant theta, you would be allowed to change it to 1 over sine theta. If you see a secant theta, you're allowed to change it to 1 over cos theta. Anything that you see, you can change to something else. So for example, in our question, we see a cos t and we see a secant t. So we could, if we wanted to, we could change the cos t to 1 over secant t. We could change the secant t to 1 over cos t. That is allowed. Our goal is to make the left side and the right side the same. And you're going to find out that a key strategy is if we look at the tools that we have already, there isn't a single one that can't be changed to either cosine or sine, or both. Right? If we go through all 6, you notice you can change cosecant to sine. We can change secant to cos. Cotangent, even though you can change it to 1 over 10, more often we'll go down to here and change it to cos theta over sine theta. And tan, you can change to sine theta over cos theta. If we change things to sine and cosine, now we're only dealing with 2 trig functions rather than 6 trig functions. And this is often a good strategy. So how does this strategy work in our first one? Well, the only one that isn't cos or sine is the secant. And so what I could do is I could say, well, secant is equal to 1 over cos. And then our fraction work comes in. Since secant is equal to 1 over cos t, and this is really over 1, can you see that we can simplify those fractions? Right? Because if you have a factor that's identical on the top and the bottom, they'll simplify. And this just becomes 1, and our puzzle is complete. We have made the left side equal to the right side. So formality number 1, we draw the line. That separates our left side and right side. We always rewrite the question first, then draw a line. Once both sides are the same, you write a statement that shows you notice they're the same. The left side is equal to the right side. And then we can add some optional fancy math stuff. I always and with the following abbreviation. How good is your Latin? Really good? Everybody speaks it at home still? Good. This is the Latin abbreviation that's often used at the end of math proofs. My Latin's terrible. I think it's quod erat demonstratum, which means what has been asked for has been demonstrated. You asked me to prove this, I prove this. So I will always end my proofs with that abbreviation, and I don't know why I did this in university, but I had a little box with shading. You can add your own little symbol to say you finished it. It's my little stamp that I finished the proof. Just kind of fun. You can add a smiley face, I don't know, whatever you like. So, this is the first one. It was really easy because all we had to do was change secant t to 1 over cos t. Okay? This page of proofs, and it is on this side, they start off easy, and by the end, they're extremely challenging. So we're going to have added techniques that we have to figure out and use as we go. Okay, but let's do, I'm going to leave you 6, 7, and let's do 8 together. Proof. And in question 8, we have sin x secant x equals tan x. So we draw our line to begin with. Make sure you use lots of space in proofs. If you try to cram a proof, it'll end up meaning that you'll have to just redo the whole thing. So first of all, if we use that strategy and say maybe my life is easier if I change things to sine and cosine, then I would think I want to change this one and I want to change this one. What can you change secant to? Secant is 1 over cos. And what can you change tangent to? Big idea. Tangent is sine over cos. And once you change it to sine and cos, it's sort of like, okay, this side is a single fraction. This side is 2 fractions multiplied by each other. How do I multiply fractions? I multiply the tops. I multiply the bottoms. And now the sides are identical. And we're done. Okay. Number 8, not so bad. Next, we're going to do number 14. And you're going to see where your fraction work really starts to come into play. Sine u over cosecant u plus cos u over secant u equals to 1. So here I have a cosecant and here I have a secant. And in this question, we're going to have lots of fractions. So I'm going to also give you some strategies for making less mistakes. That strategy is use a lot of space. In other words, intentionally, I'm going to show it with an orange box right now. Intentionally leave some space before you write the next part. I'm going to leave some space, and then in my next line, I'm going to change the cosecant u to 1 over sine u, and I'm going to change the secant u to 1 over cos u. Then I'm going to intentionally leave some space. Okay, not gonna, now that I'm gonna take that box away now, you see it has a nice little space in between. That way my fractions don't blend into each other and the top part of a question stays separate and your eyes are able to handle things a little bit better. Now what do we have here? We have fractions inside of fractions. So if we think about yesterday and the strategies that we wrote yesterday, one of the strategies if you have fractions inside of fractions is you want to try to get one fraction in your numerator and one fraction in your denominator, then you can multiply by the reciprocal. So in this first fraction, which I've circled in green here, can you see that you have actually a fraction? This is over 1. You have a fraction in your numerator, you have a fraction in your denominator, so we can multiply by the reciprocal. It will be sine u over 1, that's the top one, then flip the other one. And same thing here, this cos u would be cos u over 1, and we're dividing by a fraction, so we can multiply by the reciprocal. We'll take away this little space now. Think about adding a little space there. How do we multiply fractions? Multiply the tops, multiply the bottoms. Sine times sine will be sine squared. And remember, notation-wise, we always write the squared in between sine and u. So that would be sine squared u, and this will be cos squared u. Take that space now. I'm going to look at the whole thing, because one of these, we started, we changed everything to sine and cosine. We simplified our fractions as much as we could, and we're at sine squared u plus cos squared u, and the right-hand side is 1. So we're not done yet. They're not the same. Any ideas that you could use? This is one of our big ideas, right? So because it's one of our big ideas, you are able to, and it's on your formula sheet, if you see a sine squared u plus cos squared u, as long as the angles are the same, we can just change that to 1. And now my left side and right side are the same, so I can go left side equals right side. We're done. Yes. As I said before, for finishing a proof, often proofs end with like a little symbol. When I was in university, in one of the textbooks I had, every single proof ended with a little box, and I've just done it ever since. You can have your own little thing at the end if you like. You have to have the left side equals right side. You can add the QED because you will see that in a lot of math, so you feel like a little bit sophisticated there. And also, sometimes these proofs are so hard, you're going to really enjoy at the end going like, yes, I got it. You want to do something. So that's totally optional, but it's fun. Okay, so that is number 14. I'm going to now get you to turn to our textbooks. And we are going to do one out of our textbook. Page 607. So I'm going question 1 here, we are going to go through the difference between the words verify and prove. But the process is very much the same. In a question that says verify, you still have to split up your left side and your right side. But in a verification question, you plug in the number that they want you to verify. So secant of 30 degrees, 1 plus cos of 30 degrees, and on this side, 1 plus secant of 30 degrees. And it becomes a pie plate question, very much a chapter 6 kind of question, where we have to go to our pie plate. I know that cos of 30 degrees is root 3 over 2. That means secant of 30 degrees is 2 over root 3. And a verification question becomes a proof, but only with numbers. Is my left side and right side identical? No. Let's see if we can make them identical. So now you're allowed to use any of your algebraic strategies that you know. Combine fractions, distribute, whatever you'd like. I think in this one, what I see that would work really nice is I think I would distribute this fraction. Because 2 over root 3 times 1 is 2 over root 3. And 2 over root 3 times root 3 over 2, I hope you can see that that's going to equal 1. And are my left side and right side the same? Yes. So just like a proof. Just like a proof, you can say in a verification, I've done it. Left side is equal to right side. In a proof, very much the same. We start by rewriting the question that we want to prove. And then at the equal sign, draw the line. And in a proof, we want to get the left side and the right side the same. And we can use similar strategies. Maybe, okay, here I might distribute as well. I would get secant theta plus cos theta, secant theta. And at this point, I might want to change everything to sine and cos because I like that strategy. So if I change everything to sine and cos, the secant theta would be 1 over cos theta plus cos theta times 1 over cos theta. And on this side, I'd have 1 plus 1 over cos theta. And I have to work with fractions. Here I have a fraction multiplied by a fraction. Can you see that these factors are identical? So they would simplify. And this side would become 1 over cos theta plus 1. That matches up perfectly with the other side. So we can go that our left side equals right side. For part B, we're just going to prove. Save ourselves some time here. And we're going to actually do part B in a couple of different ways. Okay? We're going to start with the strategy I taught you because that's what's in your head. So you're like, okay, I can change everything to sine and cosine. So that would look like this. And this is not necessarily the fastest strategy, but the fastest strategy doesn't matter so much as you might like it better. But if you changed everything to sine and cosine, this is what first step would look like. On the right-hand side, you have a lot of fractions inside of fractions. On the left-hand side, you just have 1 minus a fraction. Okay? And in these questions where there's lots of fractions inside of fractions, a strategy very important strategy for this unit is we want to get a single fraction on both sides. So on the left-hand side, this technically is a fraction minus a fraction. How do you subtract fractions? You need a common denominator. What's my denominator need to be? It's going to need to be cos theta. So I would multiply the top and bottom here by cos theta. That's allowed because that's multiplying by 1. That would get my denominators the same. And on this side, I would get a single fraction of cos theta minus sine theta. I want to do the same thing on the right-hand side. And again, I'll remind you of a note that we wrote yesterday. If you have fractions inside of fractions, first, get a single fraction in your numerator and a single fraction in your denominator. Do we have a single fraction in our numerator? No. But we do have a single fraction in our denominator. Again, with so much stuff, I'm just going to remind you, leave a little space in between. I like to make my main fraction longer and thicker. I'm going to show up here that this 1, which is technically 1 over 1, I am going to multiply the top by sine theta and the bottom by sine theta, so that I get a common denominator there, and my top will become cos theta minus sine theta over sine theta. And my bottom is still cos theta over sine theta. So I left some space in between them. I have a single fraction on the top, a single fraction on the bottom. So what can I do with this? A fraction divided by a fraction is the same as multiplying by the reciprocal. Cos theta minus sine theta over sine theta multiplied by the reciprocal. Again, a little reminder of things from yesterday. We can simplify if things are multiplied and if factors are identical. So, I am not allowed in the first fraction to cancel out these signs because there's a subtraction sign. I'm going to add a set of brackets. That is one factor. That gets grouped together. And the only way something can get canceled in that is if the identical thing were in the denominator. However, we are multiplying here, and this sine theta is identical to that sine theta, so I could simplify that. This leaves me, leave space, cos theta minus sine theta over cos theta, which is exactly the same as the other side. Method 2, and this is the thing that is exciting about proofs and can also sometimes be frustrating, because you have more than one option. This is the same question, we're just going to do it again. Changing to sine and cosine and getting a single fraction, which is the technique that we just did here. I'll show it to you again. This is a super important strategy. 90% of proofs, you can get almost full marks if you know this strategy. However, sometimes when you're looking at one side or the other, there are some shortcuts that you might notice. And one of the shortcuts that can be really helpful or useful is like, hey, is there a relationship between cotangent and tangent? Yes. Tangent is 1 over cotangent. Cotangent is 1 over tangent. So the idea of the change to sine and cosine strategy is helpful because it allows you to change things to only 2 trig functions, sine theta and cos theta. However, in this question, I could have changed tan. Look at this, I can change tangent to 1 over cotangent, and now I only have 1 trig function in the whole proof. Main strategy still stays. Can you write a single fraction on both sides? This side is already a single fraction. This side, I'm subtracting. I would need to have a common denominator, so I multiply by cotangent theta and cotangent theta. And just so you know, on the exam, if you're like, oh, I'm running out of room, maybe I won't write the thetas. Maybe I'll just write cotangent, cotangent. If you forget a theta once or a variable once in a proof, automatic E3 error. Even if it's off to the side in the corner, they're really picky about it. So, because technically, cotangent without an angle actually doesn't mean anything. It'd be like, decide which letter out of your name you would be like, okay to leave out. The would be totally different kind of name if we forgot the O, right? Or we could add a letter just for fun, right? If you add a letter to your name, would be like crazy different. Violent? Yeah, that would be quite different. Okay, so now we've got our common denominator. This now becomes cotangent minus 1 over cotangent as a single fraction, and look at that. That was a lot quicker to prove this one. There we go. All right, so out of your textbook, 3, 5, 6, and 7 II, and on this page, I think you are ready, and you can do up to 20. Yes, you can do up to 20 on here, and we're going to work on those now.